So in the previous video, I talked about how to do one of these integrals where we had an even piece right here. So the question that most logically follows is, what happens if this is odd? Well, if this is odd and the tangent is odd, like this one right here, then we can integrate it with using a pretty similar technique to what we did up there. Um, you should know, well, actually, so up here we use the fact that the derivative of tangent of x is secant squared x. What I can do if I have one where it's odd and odd is use the fact that, whoops, the derivative with respect to x of secant of x is equal to secant x tangent x. And then I can pull some things out and do the same kind of strategies that we did in the previous example. So let's go ahead and do that. I have the integral of, and what I'm going to do is, oops, I'm going to get this piece so that can be my du. So I'm going to write secant x times tangent x times, and then I'm just going to write the rest of it. You can see, what do we have left? We have a secant squared x, and we have a tangent squared x, and the dx. Remember in the previous one we talked about tangent of x, or sorry, tan squared x plus 1 is equal to secant squared x. Notice if I, with this one, I know that the derivative of secant goes to secant tangent. So my goal here really, this should be squared, I'm sorry, but my goal here really is to convert everything except for the du part, or the thing that I'm trying to make the du part, into secants. So what I need to do is solve for tangent in this one. Notice tangent squared, not tangent, tangent squared, solve for tangent squared is equal to secant squared minus 1. So that means that this right here is going to get replaced with secant squared minus of x minus 1, like that. So let's do that. This is equal to the integral of secant x tangent x. And this one, you could do like side work, but I think this one happens fast enough that you don't need to do side work the way that I did it in some of the ones above. But I got secant x tangent x. This secant squared x stays the same, and then this tan x gets replaced with secant squared x minus 1 with the dx there. Now what I'm going to do, u is equal to, you guessed it, secant x, du is equal to secant x times tangent x with a dx. This, the u, will replace this and this. Notice I didn't highlight the squareds. And then this right here, secant x tangent x, which is a du, is going to replace secant x tangent x dx. So when I do my substitution, I get the integral of u squared, that is this secant squared, open parentheses, u squared minus 1, close, du. From there, it's the integral of, I'm going to distribute this into those two. So I get u to the fourth minus u squared du, which is equal to 1/5 u to the fifth minus 1/3 u cubed plus a constant. And then from there, all I got to do is sub my u back in. So this is equal to 1/5 secant to the fifth. I'm going to try and make that look like a 5 and not an s. Guess I'll do that here too. My 5s and s's are bad. Secant squared x, secant to the fifth of x minus 1/3 secant cubed x plus a constant. And now you have good techniques for integrating things that you couldn't integrate before. I think the next most logical question is to say, well, we can do these secants if it's like even and something, or we can do it if it's odd and odd, but what if it's something else? Well, sometimes you can use integration by parts, and sometimes it just gets so much more complicated that you have to use different strategies. And that's not really what this video is about. I'm just showing you new ways to do some things that will come up later on in multivariable calculus, and you should have these as part of your toolbox.